So now we'll just do a bunch of examples. Oh, the calculator part there. I'll show you the calculator part. Don't have it here. Can I borrow your, just to put it on a picture here. Yeah. So this part here that's in your notes, nicely focused. There we go. So this calculator stuff that's in your notes, what we're going to do is we're going to show how we can figure out these same answers that we've got with a couple of different calculator functions. Okay? So we'll go through each of these as we do our examples. So we'll look at this one, we'll solve it without our calculator, and then we'll check that answer with our calculator as well. So first of all, can we figure out the integral of 3 over x? So the integral of 1 over x is natural log. That 3 will just be a constant out in front. And now we plug in 5 and subtract. Plug in 2. If we type this into our calculator to see what the actual value is, 3 natural log of 5 minus 3 natural log of 2 we get 2.75 when rounded. So a couple of things. How can we find this with our graphing calculator? If this was on a non-calculator part of your test, you would just leave your answer as that 3 natural log of 5 minus 3 natural log of 2. One of the ways that you can get your calculator to show this is you can type in 3 divided by x. You can type in and graph the function that you have. So here I've graphed 3 divided by x, and I want to find out if the area between 2 and 5 is 2.75. So if you go to where you've calculated almost everything that you've ever need to calculate it with graphing, now you can go to number 7, and number 7 finds an integral. It asks for a lower limit. Our lower limit is 2. Our upper limit is 5. And it's nice because it actually shades it in for you and gives you the exact same value of 2.75. So that's the one that I like to use the most as far as it, because it's nice, it shows you a picture, it shades it in for you, so you've now found that area. The other one that was listed here, okay, so we just did the first one here with our calculator. The other one is finding fn int, so if we go to our calculator, we can hit the math button, number 9, whoa, did I hit the wrong one? Great. Clear. Math, number 9. No, I didn't hit. No, it's the right one. So here it gives you the integral sign. You want to find it from 2. Oh, I did hit the wrong one last time. 2 to 5. Your function was 3 divided by x. Now, if you have the newest version of software, this is what it's going to show up as, which is really nice because you can type it in exactly as you see it in your notes. If you have a TI-83, your version won't show up like this, and then you're going to have to follow the instructions here, that you have to write the function first, then put a comma, then an x, and then put a comma, the lower one and the upper one. So you would put you would type into your calculator, it would look like this. 3 divided by x, comma, 2, comma, 5. The comma button on your calculator is right above the 7. And it should give you that same result. If you have a TI-84 calculator and it didn't show up in the nice way that mine did, that means that you just need to update your operating system, and I can do that for you by just connecting 2 calculators. Yeah, because it's really nice when it shows up exactly as you have it in your textbook, then it's really easy to see that that's the answer. Okay? I still like doing it on the graph because then you can see what's happening with the picture. So here's our second example. Integral of, from 2 to 4 of x plus 1 over x squared dx. First of all, can you see that right now you have a function inside of another function? What that often means is you're either going to have to use substitution if you can see the derivative lying around somewhere in the same equation, or you're going to have to simplify it before you can integrate. In this case, the function that's inside, the x plus 1 over x, there's nothing outside of that. So as far as using integration by substitution, we don't have a derivative showing up. So in this case, we are going to take the time to multiply it out. I'll do it over here. So we get the integral from 2 to 4 of x squared plus 2 plus 1 over x squared dx. Put this in a box off to the side here. Now each of those things you can integrate. So when we're doing the definite integral, do each of them on their own. Maybe it would have been nice, instead of writing 1 over x squared, to write this as x minus 2, so we can add 1 to the exponent all the way through. Now we'll plug in 4. And plug in 2. Now if this was not a calculator question, what I would do as far as the math goes, before combining all my like terms and stuff inside the brackets and getting a common denominator, I might take the time to put the 64 over 3 and the 8 over 3 together. The 8 minus 6 is going to give us plus 2. The negative 1/4 plus a half will be plus a quarter, because the half is 2 over 4. And now I'm going to look and say, do I still need to get a common denominator? Yes, I will. So I'll put everything over 12. So multiply those by 4. So we get 251 divided by 12. Now we're going to check to see if this is what our calculator gives us. So going to our calculator, we're going to type in, and and I'm going to type it in without the expanded form. So x plus 1 divided by x all squared was what our original equation was. So when I hit graph, oh, fancy graph. That's what it looks like. If we want to, I'm going to just zoom this out because we're wanting to find the area between 2 and 4. So I'm going to zoom, actually I'm going to go to my window, and I'm going to change my Y max, I don't know, 15, just to see if I can see more of the graph and what's happening. So now when we find the integral number 7 from 2 to 4, get that area shaded, 22.91, we got 20.91. What did we do wrong? Everything? What happened? Did I type the equation in wrong? Did I do some mental math along the way wrong? Whoa, and this is really annoying today. Why is it doing that? Okay, we found a mistake. You don't see it? Okay, right here. How did I get this 6? Well, everybody knows that 2 times 2 is 6. Oh, there it was. Okay, so that would make this 2 more. Wow, why is this? That would make 8 minus 4, 2 more than what we had. So we have plus 4, which makes this instead of 48, 275, which makes this perfect. 22.9. Nice. Oh, I like those mental math errors when they're 2 times 2 is 6. So we get 22.9. And now we know that we haven't made up a method that's completely wrong all the way through. So I'd like you to try this one on your own. I'll put up the answer in a second. You're going to need your calculator in the end to calculate it. All right, if you want to check if you got your derivative or your integral right, and then plug in 1 and plug in 0. The natural log of 1 is 0. So if it was a non-calculator question, you would leave it as e cubed over 3 minus 2 natural log of 2 minus 1/3. If it was a calculator question and you're asked to give a decimal answer, it's 4.97. And there I've got a picture of the graphing calculator of what that graph looks like. And if you did the integration and found the shaded area, what that would look like as well. So the nice thing is with your calculator is if you've done this by hand, you have a way to check to see if that is the correct answer. So try the next one as well. And again, while doing these definite integrals, they really help you with finding integrals in general to help you study for your quiz on Thursday. All right, see how you did on this one. Integral is going to be negative cos 3x divided by 3. Still going from pi over 6 to pi over 2. When you plug those in, you get 3 pi over 2 in the first one. and it simplifies to pi over 2 in the second one. Those are values on your pi plate, and they're both 0. So you get this very interesting result of nothing. Now, if you did it on your calculator, you're going to find the following. It's going to shade that. And it has two areas that are both equal. Now, when you're figuring out rectangles, when you're actually figuring out that area, everything that's below the x-axis would have a negative height. So it's going to calculate those areas as negative areas. And this part that's below is negative, this part that's above is positive, and since they're equal in both of those sections, when we actually calculate the definite integral, we get 0. Now, when I plug it into my calculator comes up with negative 1.07, and if you would have written that on your exam as your answer, you would get it wrong. You have to be careful. What does this e to the minus 14 mean when a calculator? Times 10 to the minus 14. In other words, in scientific notation, this would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros before that 1. And what the calculator is doing is it's using an estimation technique to calculate the area. And once it gets happy that it's close enough, it stops. We know from actually doing the math that the answer is exactly 0. We're smarter than our calculator because the calculator says, I'm close enough when I get to negative decimal 0.00107. And so we've got a more accurate answer. So when you see results like that as e to the minus 14 or e to the minus 20, you can tell yourself, okay, it's basically 0.
So it's wrong on the exam prior like that?
If you were to write negative 1.07 times 10 to the negative 14, I'd hope that you would say, okay, it's probably 0. I guess technically I could make an example where that's the actual answer. I could shave off a tiny bit of the positive area, but then I would not be going from pi over 6 to pi over 2. I'd be going over from maybe 1,000 pi over 6,001 to pi over 2, something close. And if you saw that on an exam, you'd be like, oh. All right. As a non-calculator, that wouldn't be very much fun. So for our integral here, it's of the form ax plus b. So what you can do is you can add 1 to the exponent and divide by that. But then since there would be a chain rule and you'd have to multiply by a when you do the derivative, when you integrate, you're going to have to divide. So here, when you do the chain rule of 2x minus 5 to the 5 would come out in front. That cancels out with this 5 in the bottom. But you'd also have a chain rule where you'd multiply by 2, so you have to divide by 2 as well. Now this one's a little bit weird because you're going from 3 to 2. And if you actually tried to tell your graphing calculator to do the area from 3 to 2, it's going to be mad at you because you picked your lower number bigger than your upper number. But when we simplify this result, this is an equal sign in here, we get negative 2/10, which is negative 1/5. Because we took the smaller area and we subtracted the bigger area. Does that make sense? Because we did first the area up to 2, from the origin to 2, and then we did the area up to 3. So we took the smaller area and subtracted the bigger area. It would make sense that we get a negative value. If you went onto your calculator and did it from 2 to 3, you would get positive 1/5, because that would just be the bigger area, subtract the smaller one. So in this case, this part using your graph won't work, but going from 3, I'm going to just check, 3 to 2 on this part of our calculator, and we had, oh, I should have a better memory right now, 2x, is it plus 5? Minus 5 to the power of 4, right? dx. Negative 0.2. So when you use this part of your graphing calculator, it does give you the correct value. So check your integration. And you can check the values you plugged in. Negative 8.39. Well, again, what is this doing? When you calculate the area to 0, it's right on the origin, that's not going to be anything. Okay? And then when you calculate to negative 2, which is less than that, then you're going to, it's because you're doing things backwards. You're basically taking the smaller area and subtracting the bigger area. And then you're going to get a negative area as a result. So that sort of is explained a little bit in these properties. So now this is just some abstract stuff. But if, number one, if you took the integral from a to a, meaning you're not going anywhere, you're going to get an area of 0. We've already seen the result of number 2. If you do if the integral from a to b is the bigger area minus the smaller area, if you switch those and had the smaller area minus the bigger area, it's going to be negative. So if you switch the values of a and b in your integral sign, you're going to get a negative area instead of a positive area. If you wanted to, when you're finding the area between a and b, if you wanted to separate it with a new value in between a and b, point C, you could find each of those areas separately. Now this is going to be important because in some questions, like that sign one where there was an area above and an area below, if you actually wanted those two areas both to be positive and add them up, then you're going to have to do something like this later on. And we're going to have questions that's going to require us to do that. So it's nice to know that if you wanted to split your integral up into different little sections, you can do that. We've seen this before. If you have a number out in front, you can bring that outside of your integral, just like we did with indefinite integrals. You can do that with definite integrals as well. And if you're adding or subtracting two different functions, you could separate those as well. So some of the same properties we saw with the indefinite integral, we can do with our definite integral as well.